For an object undergoing translational motion, its kinetic energy is equal to half mv squared. We would expect its rotational equivalent to be half I omega squared, where I is the object's rotational inertia or moment of inertia, and omega is its angular velocity. This is actually the case, and we can prove it. Suppose we have a particle of mass m experiencing rotational motion with an angular velocity omega. Its kinetic energy is equal to half mv squared, which is half of its mass multiplied by the square of its linear velocity. We know that the linear velocity v equals the angular velocity omega multiplied by the radius of its rotation. So the kinetic energy of our particle can be written as half m into omega r squared, or half mr squared omega squared. This is the kinetic energy of a rotating particle. And so for a rotating rigid body, its kinetic energy would be equal to the sum of the kinetic energies of each of its particles. So we can write the kinetic energy of the rotating body as sigma half mr squared omega squared. Since all the particles have the same angular velocities, we can bring omega squared out. And our kinetic energy becomes 1 over 2 into sigma mr squared multiplied by omega squared. We know already that sigma mr squared equals the moment of inertia of the body. So we can write the kinetic energy of our rotating body as half I omega squared. In many cases, the motion of rigid bodies isn't purely rotational. The motion of a rigid body can be analyzed as the translational motion of the object's center of mass plus rotational motion about its center of mass. An object which rotates while its center of mass undergoes translational motion will have both translational and rotational kinetic energy, and its total kinetic energy is given as half mv cm squared plus half ICM omega squared, where VCM is the linear velocity of its center of mass and ICM is the moment of inertia about its center of mass. To understand how this can be applied, we will consider the motion of a sphere rolling down an inclined plane without slipping. At the initial position, the sphere is at the top of the inclined plane with a height h above the ground level, and it's at rest. This means that the velocity of its center of mass and its angular velocity are both equal to 0. If left free, the sphere will roll down the inclined plane. Its center of mass will experience a translational motion, and the sphere itself will rotate about its center of mass, which is its center. At the top position, the total mechanical energy of the sphere is equal to the sum of its potential and kinetic energies. So we can write our energy equation as E equals half mvcm squared plus half ICM omega squared plus mgh. Since the sphere is at rest, its translational velocity vcm and its angular velocity omega are both equal to 0. So E equals mgh. And from our conservation of mechanical energy, we know that this value of mechanical energy of the sphere will remain the same throughout its motion, since no net force or torque is applied to it. So the mechanical energy of the sphere at any height y above the ground level can be written as half mvcm squared plus half ICM omega squared plus mgy. And this is equal to mgh, which is its constant value of energy throughout its motion. The moment of inertia of a solid sphere about an axis through its center of mass is given as 2 over 5 mr squared. Substituting this into our energy equation, we have half mvcm squared plus 1 over 5 mr squared omega squared plus mgy equals mgh. Since the mass of the sphere stays constant throughout, we can factorize it from both sides and strike it out. So we're left with half vcm squared plus 1 over 5 r squared omega squared plus gy equals gh. We can rewrite this as half vcm squared plus 1 over 5 r squared omega squared equals g into h minus y. Before we proceed, we need to talk about the relationship between the translational velocity and the angular velocity of an object that rolls without slipping. To do this, we will use the motion of a rolling wheel as a case study. At the instant shown, the wheel is rotating to the right with a velocity v, which is the velocity of its center of mass. The point P, which is in contact with the ground, has a velocity relative to the ground equal to 0. If this wasn't the case, the wheel would be slipping. Relative to the center of the wheel, the point P is moving to the left with a velocity v. This means if we use the wheel as our frame of reference, we can observe its pure rotation. And since P moves relative to it, with a velocity having magnitude equal to v, its angular velocity relative to the center of the wheel is v divided by r. This is the relationship between the translational velocity and the angular velocity of an object that rolls without slipping. Going back to our problem of the sphere rolling down the inclined plane, we had our energy equation as half vcm squared plus 1 over 5 r squared omega squared equals g into h minus y. We know the relationship between our translational and angular velocity to be vcm equals omega r, or omega equals vcm divided by r. Substituting this value of omega into our energy equation, we're left with half vcm squared plus 1 over 5 vcm squared equals g into h minus y. Solving further, we can obtain vcm squared to be 10g divided by 7 into h minus y. And we can obtain vcm, which is the translational velocity of the center of mass of our sphere, as the square root of 10g divided by 7 into h minus y. When the sphere reaches the ground, we can calculate its translational velocity as the square root of 10gh divided by 7. Whenever we apply a torque to a rotating body, its rotational kinetic energy changes. The work done by a torque applied on a rotating body is equal to the integral of the torque with respect to its angular displacement, from its initial angular displacement to its final angular displacement. If the torque is constant, the work done is equal to the magnitude of the torque multiplied by the change in the object's angular displacement. Similar to the translational case, the work done by a torque on a rigid body is equal to the change in its rotational kinetic energy. So we can write that work done equals half I omega 2 squared minus half I omega 1 squared, where omega 2 and omega 1 are the final and initial angular velocities respectively. This is the angular or rotational equivalent of the work energy principle.